ETOPS stands for Extended Range Twin Engine Operations. It is a regulatory framework to control the conduct of operations of twin-engined aircraft when their route takes them a long distance from the nearest diversion. Let's start by first considering normal non-ETOPS operations. The majority of transport flights take place over routes where there are many en route alternate aerodromes. In the event of an emergency requiring an in-flight diversion, there are usually several available. Where there are no en route alternates, we have a procedure to establish point of equal time, otherwise known as critical point. However, proceeding for a long period with one engine out carries risks which have to be regulated and minimized. Traditionally, such operations were considered unacceptable for twin-engined aircraft. For this reason, before 1985, long-range oceanic flights had to be carried out by 3 or 4 engine aircraft. Under EASA rules, unless specially authorized by the controlling authority, a Performance Class A public transport twin-engined aircraft shall not fly a route that takes it more than 60 minutes flight time at its one engine out speed from an alternate. This is laid down in CSOPS, which was formerly known as JAROPS. Clearly, this imposes operational limitations. Here is the direct route from London to New York. This can be flown by 3 or 4 engine aircraft. However, consider a twin-engined aircraft. Let's put in some alternate airports. And now we'll draw in some circles representing 1 hour's flight at the one engine out true airspeed. You can see that this route leaves a gap between Shannon and Gander. A twin-engined aircraft not covered by ETOPS regulations would therefore have to fly this longer route in order to stay within the 1 hour range circles. This adds to cost and the time. This situation changed from the early 1980s onwards, when more powerful and reliable engines were developed. It became possible to build twin-engined aircraft capable of carrying large numbers of passengers over thousands of miles. Manufacturers and operators lobbied that the chances of an engine failing in flight were now extremely low, and also that in the unlikely event of an engine failure, a twin-engined aircraft could still safely operate on one engine for longer periods than 1 hour. This argument was accepted, and the regulations were changed, allowing the first ETOPS flight to take place in 1985. However, the regulation and control of such flights is extremely stringent. Each operator requires an individual ETOPS approval from its National Aviation Authority, and only certain approved aircraft types can be authorized. Let's look at some of the definitions used in ETOPS. Firstly, ETOPS itself. The letters stand for Extended Range Twin-Engine Operations. It is defined as those operations intended to be, or actually conducted by twin-engined aircraft over a route that contains a point further than 1 hour's flying time in still air at the normal one engine in operative speed from an adequate aerodrome. We shall look at the definition of an adequate aerodrome shortly. We therefore need to define the normal one engine in operative speed. The operator is required to determine a speed for the calculation of the maximum distance to an adequate aerodrome for each two-engine type. This is not necessarily the exact speed which would occur on the occasion of any particular emergency, since that would vary with weight, temperature and altitude. However, it is the speed to be used for all planning and should cover the typical worst case. It has to be defined in the operator's flight operations manual, and, for most current ETOPS-capable aircraft, is around 380 knots true airspeed. The threshold time is the maximum time that a twin-engined aircraft is permitted to fly on one engine on any route unless it is governed by ETOPS regulations. it is 60 minutes. Alternatively, it may be defined for some operators as a threshold distance, in which case it is the distance travelled in still air in 60 minutes at the normal one-engine inoperative cruise speed. However, where an ETOPS extension is granted, the rule time is used. This is defined as the maximum time at the normal one-engine inoperative speed that any point on the route may be from a suitable aerodrome for landing. Again, we will look at the definition of a suitable aerodrome shortly. Alternatively, this may be quoted as a rule distance, in which case it's the distance travelled at the normal one-engine inoperative speed in the rule time. The ETOPS entry point is that point along the track where the aircraft first passes the threshold distance from any adequate aerodrome. The ETOPS exit point is that point along the track where the aircraft is last more than the threshold distance from any adequate aerodrome. The ETOPS segment is that portion of the route where the aircraft is more than the threshold distance from any adequate aerodrome. This may alternatively be known as the ETOPS sector. ETOPS regulations are applicable only over the ETOPS segment. We now come to the definitions of an adequate aerodrome and a suitable aerodrome. Firstly, an adequate aerodrome. For every proposed ETOPS route, the operator must compile a list of alternate aerodromes to be used. These must be approved by the operator's National Aviation Authority and listed in the Company Flight Operations Manual. The runways must be long enough for the operator's aircraft types and must have a suitable surface and load-bearing capacity. The runway lighting must meet approved standards. There must be adequate air traffic controls facilities. Communications equipment must meet certain standards. There must be navigation aids and an instrument approach and letdown aid, ILS or ground radar. There must be appropriate weather reporting facilities. And fire and emergency services must meet requirements for the number of passengers to be carried. Neither the company nor the aircraft commander of any flight has the authority to use any other alternate aerodrome on this route without approval from the National Aviation Authority, followed by an amendment to the Company Flight Operations Manual. So, what is the difference between an adequate aerodrome and a suitable one? For any particular flight, the aircraft commander selects from this list of adequate aerodromes the ones that he will nominate as his alternates. Their weather must be forecast to be within limits at the time. The navigation and letdown aids must be serviceable. The fire cover must be in place. And each aerodrome must be open from 1 hour before it might first be needed until 1 hour after it might last be needed. These become the suitable aerodromes for that flight and are nominated on the ATC flight plan. We said earlier that ETOPS flights are subject to more stringent regulation and control than normal non-ETOPS operations. It is a requirement to compile a minimum equipment list for any public transport operation. However, for ETOPS operations, the existing MEL must be re-evaluated and adjusted as necessary to reflect the higher safety standards required for prolonged operation on one engine. These will include reappraisal of such systems as hydraulics, electrics, instrumentation, fire suppression, air conditioning and pressurization, and many others. Critical point is always an important consideration in any flight which takes place a long distance from alternates, whether ETOPS or not. The easiest method of calculating it, and certainly the one you should use for exam questions, is the equation that x equals dh over O plus h. However, there are many other ways of establishing it. One of them is by use of the Jeppesen North Atlantic Plotting Chart, Chart NAP in the Jeppesen Manual. The chart has a number of circles centered on various airfields. The dotted lines represent a rule time of 180 minutes flight time, and the solid lines represent a rule time of 120 minutes and a distance of 820 nautical miles. A TAS of 410 knots has been assumed. In the centre of the chart is a line with an arrow at each end. The left arrow points to Charlie Yankee Quebec X-ray, which is Gander, and the right one to Echo India November November, which is Shannon. The orientation of the arrow is the great circle track between Shannon and Gander, and the figure 1715 is the total distance between them. The vertical line through the figure shows the halfway point. At the bottom right-hand corner of the chart is a diagram which can be used to calculate the position of the equal time point. We use the normal convention of positive for a tailwind and negative for a headwind component to plot the outgoing and returning wind components. The intersection of the two lines gives an equitime number. The instructions tell us that if we multiply this number by 1% of the distance between the two aerodromes, the product is the difference that the equal time point is displaced from the midpoint. Positive moves the point in the continuing direction and negative in the returning direction. Here is a worked example calculating the equal time point, assuming a tailwind component of 30 knots from Shannon and a headwind component of 30 knots back to Shannon. Plot the two lines as shown on the screen. The intersection of the two lines gives an equitime number of -3. As the total distance between Shannon and Gander is 1715 nautical miles, 1% is 17.15. Multiplying by -3 gives a distance of -51.45. As the answer is negative, we move the equal time point 51.5 nautical miles in the returning direction. This is towards Shannon. The distance markers on the arrow between Shannon and Gander help us plot the position. This is a quick and simple way of adjusting the equidistant point for wind component to make it the equal time point, or critical point. The Jeppesen graphical method of establishing critical point requires the graph to be included on the published chart. Additionally, it is valid for only one TAS, which may not be the one that our aircraft uses. A method that can be used on any navigational chart and for any TAS utilizes direct plotting of the wind vector. We start by plotting the still air critical line, which is the halfway mark. We now work out the time taken in still air to fly to either aerodrome at the one engine out speed. The distance from Shannon to Gander is 1715 nautical miles, so the distance from the halfway point to either of them is 857.5 miles. At the typical one engine out TAS of 380 knots, this would take 2 hours and 15 minutes. We now apply the wind vector. As an example, we shall assume that the forecast wind velocity is 315 at 50 knots for the whole of the route. However, this is just 1 hour's worth of wind. From the critical point, the aircraft would be in this wind for 2¼ hours. We therefore need to expand our wind vector by this factor. 50 knots for 2¼ hours gives a vector length of 112.5 nautical miles. We plot this upwind from the still air critical line, that is, the equal distance line. This gives us the wind-adjusted equal time line. As you can see, we have moved the critical line in the direction that the wind is coming from, exactly as we noted in our opening lesson on point of equal time. Additionally, we have not had to convert the wind velocity into a wind component. The geometry of the plotting takes into account the angle between the track and the wind direction. This plotting method is particularly useful because it is the only one, apart from computer-based solutions, which can deal with critical points between multiple bases. Take this situation. You are flying from Muscat in Oman to Malé in the Maldive Islands. You select, as your en route alternate, Mumbai in India. Clearly, for the first part of your route, your nearest diversion is Muscat. Somewhere in the middle you would be better off going to Mumbai. And towards the end you should go to Malé. How do we calculate where these changeover points occur? There is obviously one equal time point between Muscat and Mumbai, and another one between Mumbai and Malé. We use a graphical solution. We draw a construction line between Muscat and Mumbai, and then add the perpendicular bisector so that it meets the track. We have now constructed an isosceles triangle. This distance here must be the same as this distance here. This gives us an equidistance line here. We now need to correct for the wind. Let's assume that the wind is from 240 at 30 knots and that the still air flight time to either alternate is 1.5 hours. This gives us a total vector of 240 at 45. We apply this to get the equal time line. Now, carry out the same exercise between Mumbai and Malé. First, the construction line. Then, the perpendicular bisector. Here's our isosceles triangle, with this side the same length as this side. Again, we apply our wind velocity factored for the appropriate flight time to get equal time point 2. So in this part of the route we would return to Muscat. Here we would divert to Mumbai. And here we would continue to Malé. Fuel policy also needs to be closely addressed for ETOPS operations. Imagine an aircraft on an ETOPS segment between Shannon and Gander. The aircraft has arrived at the critical point and the flight is proceeding normally and there is no emergency. How much fuel is required to complete the flight? Firstly, we need the trip fuel for the remaining part of the flight. We also require the remaining contingency fuel, which is usually 5% of the remaining trip fuel. Alternate fuel is required, and we also need to have final reserve fuel. Let's assume that, as an example, this amount comes to a total of 6,800 kilograms. Now imagine the aircraft to be back at the critical point, but this time we have an engine failure. The aircraft will drift down to its stabilizing altitude. The actual altitude on the day will depend on weight and temperature, but for most modern airliners it will be in the medium to high 20,000s of feet. We will assume that it is flight level 250. The lower altitude and slower true airspeed will result in a longer flight to the alternate and an increase in the fuel required. If the aircraft had proceeded back from the critical point, it would have taken the same time and used a very similar amount of fuel. However, a pressurization failure could be a worse case. It would be essential to initiate an immediate descent to flight level 100. This would reduce the speed and increase the fuel consumption still more. This would be followed by a letdown and an instrument approach to the airfield. And again, if the aircraft had proceeded back instead of onwards from the critical point, it would have taken the same time and used a very similar amount of fuel. A pressurization failure might be caused by a leak or mechanical failure, in which case both engines would still be available. However, it might be that an engine had failed and the one which had failed was the one which powered the pressurization system. Each of these situations uses a different amount of fuel and we have to cover the worst case. The rules for the required fuel following an engine failure are not quite the same as the normal case. We need the remaining trip fuel, but this time for the descent, the transit at flight level 100 and the second descent to 1500 feet, plus the normal 5% contingency fuel. We don't need alternate fuel. We are already diverting. The remaining trip fuel and contingency fuel has become the alternate fuel. We still need final reserve fuel, but it is assumed that if you've just flown halfway across the Atlantic on one engine, you'll get a certain amount of priority when you arrive. Final reserve fuel is therefore reduced to 15 minutes instead of the usual half hour. In addition, we are required to have fuel for an instrument approach, which may not be successful, so we'll also need the fuel for a missed approach procedure, another instrument approach and a landing. Will this amount of fuel come to more than the amount we would have needed if the flight had proceeded uneventfully? That was 6,800 kilograms. The answer is that it depends on the circumstances. There are many variables. If the aircraft had been proceeding to Los Angeles after passing Gander, there would have been plenty of remaining normal trip fuel. However, if it had been going to Gander or Montreal, there would not. The number of engines available to us will also make a difference. One engine is usually more economical than two, but if both are working normally following a pressurization failure, you would not plan to shut one down in order to save fuel. There are other factors as well. Weight, temperature and the requirement for anti-icing will all affect the calculation. We have to work it out for the worst case. In this example, we are going to assume that the fuel required is 7,600 kilograms. This amount is known as the critical fuel. The difference between the critical fuel and the normal fuel is called additional fuel and has already been covered earlier in the course as part of basic fuel policy. In this example, the additional fuel would be 800 kilograms. CAP 697 gives us the data to calculate critical fuel for the Boeing 737-400. The relevant graphs are figure 4.7.1 alpha on page 73, which is for the one engine case, and figure 4.7.1 Bravo on page 74, which is for two engines. These are used for pre-flight planning to establish critical fuel. Therefore, notice that at the bottom it says, distance to diversion airport from critical point. The calculation is from the critical point, not the actual point of diversion. This covers the worst case. Let's see what they include. For the all engines operative case, the white box at the top left says, emergency descent to 10,000 feet, level cruise at 10,000 feet. 250 knots indicated airspeed, descent to 1500 feet. 15 minutes hold at 1500 feet. 1 missed approach, approach and land. 5% allowance for wind errors. For the one engine in operative case, it is the same except for the last line where we have the words includes APU fuel burn. This is because the engine which has failed may be the one which supplies essential services such as electrics or hydraulics. If so, we may need to have the auxiliary power unit on to keep these going. So, now let's see how they are used. We'll assume that the critical point is 600 nautical miles from the alternate to be used. There is 50 knots headwind and that the aircraft total weight at the critical point is 50,000 kilograms. Icing is forecast at 10,000 feet. We enter the one engine inoperative graph at the bottom at 600 nautical miles distance from critical point to diversion airport, and go vertically to the wind reference line. We then follow the wind trade lines up to 50 knots headwind. Then we go vertically to the sloping line for the appropriate weight at the critical point, 50,000 kilograms in this example. Then travel horizontally to the right-hand edge and read off the fuel, which, in this case, is 6,100 kilograms. But remember, icing was forecast. Read the second and third lines under the graph. If icing conditions exist, increase fuel required by 20% to account for engine and wing anti-icing on, and ice accumulation on unheated surfaces. 6,100 plus 20% comes to 7,320 kilograms. However, we haven't finished yet. Read the last two lines under the graph. They say, compare the fuel required from this chart with critical fuel reserves for 2 engines operative. Use the higher of the two. So now we do it all again with the all engines operative graph. This time we get 6,300 kilograms before allowing for icing. But the icing correction figure is 18% for the 2 engine case. 6,300 plus 18% comes to 7,434 kilograms. So we take the worst case. Not surprisingly, 2 engines use more fuel than 1, though perhaps it is surprising that they use so little more. Our critical fuel is 7,434 kilograms. There is just one other feature to point out before leaving the use of this graph. The fuel burn is for ISA conditions. For every 10 degrees hotter than ISA, we add 0.5% to the fuel. That's not 5%, it's 0.5%. So, for instance, if the graph figure was 6,000 kilograms and the temperature were 20 degrees above ISA, we'd add 1%. This would give a final figure of 6,060. We also need to be able to use the area of operation table at figure 4.7.2 on page 75 of CAP 697. The ETOPS area of operation is defined as the area within which the operator is authorized to conduct extended range operations. This area will be specific to each route. For instance, the distance from Shannon to Gander is 1,715 nautical miles. Therefore, the area of operations will be half that figure, 858 miles. The maximum distance to any diversion within the rule time can be found from figure 4.7.2. This is based on ISA conditions in still air, 1 engine inoperative and a drift down to stabilizing altitude starting at or near the optimum altitude. The left column groups the table into the speeds to be flown for the drift down. For the first, for instance, the aircraft is held at Mach 0.7 until the indicated airspeed reaches 280 knots. The bottom one is for operation with the flight management computer, which has a facility to calculate long-range cruise drift down on 1 engine. We enter via the left-hand 2 columns with the drift down parameters and the weight at the start of the diversion. We will use Mach 0.7 and 280 knots and a start weight of 50,000 kilograms. If the rule time is 120 minutes, the maximum diversion distance is 768 nautical miles. Finally, we come to the in-flight diversion graph. This is different from the 2 we looked at earlier. You will remember that they were for planning purposes and were from the critical point to establish the critical fuel. However, that was for planning to cover the worst case. If a crew experiences an in-flight emergency, they are not going to proceed to the critical point. They will divert from wherever they are. Figure 4.7.3 on page 76 is for in-flight diversion. Note that the caption at the bottom says, "Distance from point of diversion to alternate." It works just like all the other simplified fuel planning graphs. We will use the following figures as an example. Distance to diversion, 800 nautical miles. Weight at start of diversion, 45,000 kilograms. Stabilizing altitude, flight level 260. 50 knots tailwind. Temperature is ISA -10. And if we follow the lines in the usual way, we get 3,700 kilograms and 2 hours flight time. Note that this is the actual fuel burn, including the APU burn. There is no contingency fuel or any of the other reserves that we had in the planning graph. You simply subtract the figure obtained from the graph from your current gauge reading to get the expected fuel on arrival at the destination. Any airline which is sophisticated enough to operate ETOPS will use computer flight planning. Here is a route. We've seen it before. It's from Muscat, which has the ICAO code Oscar Oscar Mike Sierra, to Male, which is Victor Romeo Mike Mike. Our en route alternate is Mumbai, or Victor Alpha Bravo Bravo. There is an equal time point between Muscat and Mumbai, where the time back to Muscat is the same as the time to fly to Mumbai. And there is a second equal time point between Mumbai and Male, where the time to Mumbai is the same as the time on to Male. This is what the computer flight plan looks like. Block 1 tells us that the time from takeoff to equal time point 1 is 1 hour 30. And from takeoff to equal time point 2 is 2 hours and 18 minutes. Block 2 gives us the calculated position of equal time point 1 and tells us that it is between Muscat and Mumbai. If we go back to Muscat, our minimum off-route altitude or safety altitude will be 9,700 feet. If we divert to Mumbai, the safety altitude will be 7,700 feet. The track back to Muscat is 325 and on to Mumbai is 072. Do these look right? Let's look at the route. This should be 325. That looks about right. And this should be 072. That looks good as well. The planned flight levels are 100 in each case, to cover a pressurization failure. And here are the distances. Note that they are close, but not identical. This is the effect of wind. And here are the times. These have got to be the same. The one-engined IAS is 320 in each case. But the TASs are different. The one to Mumbai is slightly higher. Why do you think this is? After all, the flight levels and IASs are the same. You should have realized that the track to Mumbai is further south and therefore nearer to the equator. The temperature is likely to be hotter. For the same IAS, this will give a greater TAS. The ground speeds are close but not identical. As before, you would expect that because of the effect of wind. And the one-engine fuel burns are slightly different, again because of the temperature difference. The computer then compares these one-engine fuel burns with the normal route fuel, and in this case, no additional fuel is required. Strictly, this should be called additional fuel, and critical fuel should refer to the one-engine fuel burn, but the meaning is obvious here. And finally, in Block 1, we have our fuel burns for the two-engine case at flight level 100. For this aircraft, they are very slightly less than the single-engine case. We now move to Block 3. This gives us the predicted fuel at equal time point 1. If we have no contingency fuel, it is 17,083 kilograms. However, if we have all the contingency fuel remaining, we will have 17,956. Block 4 tells us that no allowance has been included for anti-icing. Again, no surprises there. We are close to the equator. However, there is a 4.1% factor included for the performance degradation of this particular aircraft. This figure will have been established from past flights. Now let's look at Block 2A. This is the equivalent of Block 2, but for equal time, point 2. Note that equal time point 1 was at about 16 north, but this is at 11 north. This is what you would expect from looking at the route. It's between Mumbai and Malé. Look at the safety altitudes for these two. Mumbai's is 7,700 as before, but why do you think Malé's is so low? You should be able to work it out. The Maldive Islands are a group of coral atolls and they have an average elevation of 5 feet. The highest elevation on the islands is 8 feet. 300 feet has been added to cover unknown buildings, and then a 1,000-foot safety factor has been applied to give 1,300 feet. Let's check that the tracks look sensible. From equal time point 2 to Mumbai should be 031, and to Malé should be 142. They look all right. The rest of Block 2A and Blocks 3 and 4A follow a similar pattern to Blocks 2, 3 and 4. This has been a demonstration of how to check a computer flight plan. Nobody expects you to recalculate all the figures, that's what the computer's for. But you should be able to understand the reasons for the data that you see, and you should be able to explain them to yourself and to pick up any apparent discrepancies. You'll remember that we said at the start of this lesson in discussing suitable aerodromes that they have to be available from 1 hour before they might first be needed until 1 hour after they might last be needed. This also is covered in the computer flight plan in Block 5. Let's start with equal time point 1. This is the last point at which we could possibly divert back to Muscat. We'll be able to work out that, if we did, we would arrive at Muscat at 2:17. However, equal time point 1 is also the first point at which we could possibly divert to Mumbai, and because it is an equal time point, we would arrive at either Muscat or Mumbai at the same time. That time must be 2:17. We can see this because we notice that Muscat must be open until at least 3:17, and that Mumbai must be open from 1:17. Similarly, equal time point 2 is the last point at which we would divert to Mumbai. It's also the first point at which we would divert to Malé. The arrival time, either way, must be 03:05. Therefore Mumbai must be available until at least 04:05. And Malé must be available from at least 02:05. Let's summarise this lesson. ETOPS is a regulatory framework to control the conduct of operations of twin-engined aircraft when their route takes them a long distance from the nearest diversion. Under EASA rules, unless specially authorised by the controlling authority, a Performance Class A public transport twin-engine aircraft shall not fly a route that takes it more than 60 minutes flight time at its one-engine outspeed from an alternate. ETOPS is defined as those operations intended to be, or actually, conducted by twin-engined aircraft over a route that contains a point further than 1 hour's flying time in still air at the normal one-engine inoperative speed from an adequate aerodrome. The regulation and control of ETOPS flights is extremely stringent. Each operator requires individual ETOPS approval from its National Aviation Authority, and only certain approved aircraft types can be authorised. An adequate aerodrome is one selected by the operator and listed in the company flight operations manual, whereas a suitable aerodrome is one selected by the commander of the flight from the list of adequate aerodromes. The minimum equipment list requirements are more stringent than normal operations, and the calculation of critical points becomes extremely important. Make sure that you are familiar with the use of the Jeppesen graph. Although any ETOPS operator would in fact provide the pilots with computer-generated calculations, possibly including several alternates. It is necessary to establish what the critical fuel is and whether an uplift of additional fuel is required. You need to be familiar with the use of the critical fuel graphs on pages 73 and 74 of CAP 697. And the area of operations table on page 75, and the in-flight diversion graph on page 76. These are all examined. We finished by looking at an ETOPS computer flight plan to bring these ideas together and to show you how to give the flight plan a quick common sense check. And we emphasized that any suitable aerodrome must be available from 1 hour before it might be first needed until 1 hour after it might last be needed.